Hello and welcome to your ultimate guide for the C165 OA Integrated Physical Science course. My goal today is simple: give you everything you need to fully understand the key concepts, master them, and walk into your C165 OA exam with total confidence. In this video we'll cover scientific methods, physics concepts, chemistry fundamentals, earth science and astronomy topics. And remember, our website offers free exam guides and practice questions to help you ace your C165 OA exam. You'll find the link in the description below, so be sure to check it out and get the resources you need to study smarter, not harder. So let's dive right in. Let's begin with the very foundation of how we know what we know, the attributes of science. What makes something scientific? Science isn't just a collection of facts, it's a process, a way of understanding the world. At its core, science studies the natural world. It uses ideas that can be tested through observation and experimentation. This is a crucial point. A scientific idea must be falsifiable, meaning there has to be some conceivable experiment or observation that could prove it wrong. For example, the statement, "All rocks fall when dropped," is scientific because we can test it. If we dropped a rock and it floated upwards, the statement would be proven false. In contrast, a statement like "invisible demons make rocks fall" isn't scientific because there's no way to test for the presence or absence of invisible demons. Science relies on data gathered from these observations and experiments. It's not about opinions or beliefs, it's about evidence. Often this work is presented to the scientific community for evaluation, a process called peer review, which helps ensure the quality and validity of the research. And finally, good science almost always leads to further questions and new avenues of research. It's a never-ending cycle of discovery. This process of discovery can take many forms, and it's a common misconception that there's a single, rigid, scientific method that all scientists follow step by step. In reality, scientific investigations are diverse. They can be sparked by imagination, a hunch, or even pure luck. However, all scientific investigations, regardless of their form, share the goal of producing knowledge that reflects natural reality as closely as possible. One of the most common types of investigation is the controlled experiment. This is the classic setup you might picture in a physics or chemistry lab. Scientists perform a controlled experiment when they want to find out how changing one thing causes something else to change. The key here is control. In a simple controlled experiment, a scientist intentionally changes one quantity, which we call the independent variable, and observes how another quantity, the dependent variable, changes in response. All other conditions, which we call control variables, are kept exactly the same. For example, imagine you want to know how different types of soil absorb water. The type of soil is what you are purposefully changing. So that's your independent variable. The time it takes for the water to be absorbed is what you are measuring, and it depends on the soil type, making it the dependent variable. To make it a fair test, you'd use the same amount of soil, the same amount of water, and keep the temperature the same for each test. Those are your control variables. Failing to control these other variables could lead to false conclusions. Before we dive deep into our first major concept, I want to let you know about something that's going to be incredibly valuable for your exam preparation. I've created over 300 completely free practice questions that work hand in hand with everything we're covering in this comprehensive guide. You'll find the link in the description, and I really encourage you to bookmark it because these questions will help you apply every concept we discussed today. Now, not all scientific questions can be answered with a controlled experiment in a lab. You can't exactly create a solar system in a beaker or build a volcano in a classroom to study it. For questions like, what causes the sun to shine? Or how do mountain ranges form? Scientists rely on observational studies. In these studies, researchers observe systems as they appear in nature without trying to change them. Much of astronomy and earth science is built on observational studies. Galileo's discovery of Jupiter's moons in 1608, using one of the first telescopes, was a landmark observational study that changed our view of the universe. He didn't manipulate Jupiter, he simply observed it. Another powerful example is Darwin's theory of evolution. His meticulous field observations of species variation and survival form the basis for the concept of natural selection. These observations were later supported by controlled experiments in genetics, but the initial breakthrough came from watching nature. The theory of plate tectonics also began with an observation by Alfred Wegener, who noticed that the coastlines of continents like South America and Africa fit together like puzzle pieces. While his idea was initially rejected, further observational evidence, like the discovery of the Mid-Atlantic Ridge, eventually confirmed his core concept. The challenge with observational studies is the lack of control. Hidden variables that aren't measured can sometimes suggest a relationship between two things where none actually exists, so researchers must be very careful when drawing conclusions. Whether through experiments or observations, scientists gather data. To make sense of this data and explain how things work, they create models. Models are essential for things we can't see directly, whether they're too small, like atoms, too far away, like distant galaxies, or abstract concepts like gravity and energy. A good model explains current observations and, crucially, predicts new ones. There are several types of models. Physical models are tangible representations, like a model of the solar system with spheres for the Sun, Earth, and Moon. This kind of model is great for showing how eclipses happen or how the Moon's phases work, even if the distances aren't to scale. A wind tunnel is another physical model, a scaled-down version used to study how air moves around objects like airplanes or cars. Conceptual models help us visualize the unseen. The classic model of an atom with electrons orbiting a nucleus like planets is a conceptual model. While we now know electrons behave more like clouds of probability, this simple model is still incredibly useful for understanding basic atomic structure and chemical bonding. Mathematical models use formulas and graphs to describe phenomena. The equation of a wave, for instance, is a mathematical model that describes its amplitude and wavelength. Finally, computer models are becoming increasingly powerful. Supercomputers can model incredibly complex systems, like the formation of the universe or global climate patterns, by processing trillions of pieces of information. These models allow scientists to run simulations, compare the results to real-world observations, and refine their understanding. A key thing to remember is that all models are simplifications and are subject to change as our knowledge grows. Columbus used a spherical Earth model to sail west to India, which was correct in principle, but his parameters for Earth size were wrong. Luckily for him, the Americas were in the way. Today, our models are much more precise. After a scientist collects data, they need to interpret it. One of the most common tools for this is a scatter plot, which shows the relationship or correlation between two variables. Typically, the independent variable, the one the experimenter controls, goes on the horizontal x-axis. The dependent variable, the one that changes in response, goes on the vertical y-axis. When we plot data, we often look for patterns. One common pattern is direct proportionality, also known as a positive correlation. This is when two variables are linked in such a way that as one increases, the other increases proportionally. The graph of this relationship is a straight line sloping upwards. A simple example is the cost of food sold by weight. As the weight of the cheese you buy increases, the price increases at a constant rate. This can be represented by the equation y equals kx, where k is the constant of proportionality. Another example is the distance a car travels at a constant speed over time. More time equals more distance. The opposite of this is inverse proportionality, or a negative correlation. This happens when an increase in one variable causes a proportional decrease in another. The graph for this relationship is a curve that slopes downward, often a shape called a hyperbola. The equation here is y equals k divided by x. A great real-world example is travel time and speed. If you need to travel 100 miles, the faster your speed, the less time it will take. As speed goes up, time goes down. Another example is elevation and air temperature. As you climb a mountain, increasing your elevation, the temperature generally decreases. Sometimes, of course, there is no relationship at all. This is called no correlation. The data points on a scatter plot will look randomly scattered with no discernible trend. For example, there is no correlation between the amount of sugar a person eats and their intelligence. One very important point for your C165 OA exam is to distinguish between correlation and causality. Just because two variables are correlated on a graph does not mean one causes the other. Time is often used as an independent variable. A graph might show that global temperatures have increased over time, a positive correlation. But time itself doesn't cause warming. There's a hidden variable, increasing greenhouse gas emissions, which are also correlated with time. The emissions are the cause. Never assume causation from correlation alone. What we just covered about data interpretation is exactly the type of material you'll find in our free practice question bank. These aren't just basic questions either. They're designed to test your deep understanding, just like the real OA exam will. To conduct these experiments and gather data, scientists need a standardized way to measure things. This is where the International System of Units, or SI system, comes in. It provides a universal language for measurement that allows scientists worldwide to share and compare their data. The SI system is built upon 7 base quantities. You'll want to be familiar with these for the C165 OA exam. Length is measured in meters, m. Mass, which is the amount of matter in an object, is measured in kilograms, kg. It's crucial not to confuse mass with weight. Your mass is the same on Earth and on the Moon, but your weight, which is the force of gravity on your mass, is much less on the Moon. Time is measured in seconds, ms. Temperature is measured in Kelvin, K. The amount of a substance, especially for tiny things like atoms, is measured in moles, mole. Electric current is measured in amperes, amp. And the brightness of light as perceived by the human eye is measured in candelas, CD. The SI system also uses prefixes based on powers of 10 to handle very large or very small numbers. You've seen these before. Kilo for 1,000, milli for 1,000th, micro for 1,000,000th, and so on. For example, instead of writing 0.001 meters, we can simply write 1 millimeter. From these 7 base units, we can create derived units for other quantities. Speed, for example, is a derived quantity. It's defined as distance travelled per unit of time. So its SI unit is meters per second, written as ms. Area is another derived quantity. For a rectangle, you multiply length by width. In SI units, that's meters times meters, which gives you square meters, or m squared. Volume is the amount of space an object occupies. For a box, it's length times width times height, giving a derived SI unit of cubic meters, or m cubed. In a lab, you'll often see volume measured in litres or millilitres, which are also derived units. Density is another important one. It's mass per unit volume, so its SI unit is kilograms per cubic metre, kgm cubed. A key concept about density is that it's an intrinsic property of a material. A small gold nugget and a large gold bar have the same density because even though the bar has more mass, it also has proportionally more volume, so the ratio of mass to volume stays the same. Let's dive deeper into the physics of motion, starting with speed, velocity, and acceleration. These are concepts you'll definitely see on the C165 OA exam. Speed, as we've mentioned, is how fast an object is moving. It's a scalar quantity, which means it only has a magnitude or a size. If a car is going 60 miles per hour, that's its speed. Velocity, on the other hand, is a vector quantity. This is a critical distinction. A vector has both magnitude and direction. So for velocity, you need to know not just how fast, but also in what direction. A car's velocity might be 60 miles per hour due east. 2 cars can have the same speed, but different velocities if they are travelling in different directions. Now, what happens when velocity changes? That's acceleration. Acceleration is the rate of change of velocity. And since velocity includes both speed and direction, you can accelerate in 3 ways: by speeding up, by slowing down, which is sometimes called deceleration, or by changing direction. That last one is a common trip-up. A car driving in a circle at a constant speed is still accelerating because its direction is constantly changing. A ball rolling to a stop is accelerating because its speed is decreasing. Understanding that acceleration is any change in velocity is key. So what causes acceleration? In a word, force. In physics, a force is simply a push or a pull. You can't see a force, but you can see its effects. When you push a grocery cart, it accelerates from rest. An object will accelerate only if a net force is acting on it, and the acceleration will be in the same direction as that force. Forces are vectors, just like velocity. They have a magnitude or size and a direction. In the US, we often use pounds for force, but the SI unit of force is the Newton, abbreviated N. 1 Newton is about the weight of a small apple. It's also important to remember the difference between mass and force. Kilograms are a unit of mass, while newtons are a unit of force. Your mass doesn't change, but the force you exert can. I know we're covering a lot of detailed information, and you might be wondering how to practice applying all these concepts. That's precisely why I put together those 300 plus free practice questions I mentioned earlier. They'll help you work through problems that combine multiple concepts, just like you'll see on the actual exam. Now, it's rare that only one force acts on an object. Usually there are multiple forces. The overall effect is determined by the net force, which is the combination of all forces acting on an object. If forces act in the same direction, they add up. If you push a box with 10 newtons of force and a friend pulls it in the same direction with 20 newtons, the net force is 30 newtons in that direction. If forces act in opposite directions, you subtract them. If you push the box with 20 newtons to the right, and your friend pushes with 16 newtons to the left, the net force is 4 newtons to the right, in the direction of the stronger force. What if the forces are equal and opposite? If you both push with 20 newtons, the forces cancel out. The net force is 0. These are called balanced forces. Balanced forces do not cause a change in motion. An object with balanced forces acting on it will not accelerate. This leads us directly to one of the most important principles in all of physics, Newton's first law of motion. Newton's first law, often called the law of inertia, states that an object will remain at rest or continue to move at a constant velocity unless acted upon by a non-zero net force. In other words, objects resist changes in their motion. This tendency to resist changes in motion is called inertia, and the measure of an object's inertia is its mass. An object with more mass has more inertia. It's harder to start moving a large boulder than a basketball, and it's harder to stop it once it's moving. This is because the boulder has more mass, and therefore more inertia. A full shopping cart is harder to push, stop, or turn than an empty one because it has more mass. So Newton's first law tells us that if you see an object accelerating, speeding up, slowing down, or turning, there must be a non-zero net force acting on it. If the net force is 0, the object's velocity remains constant. If it's at rest, it stays at rest. If it's moving, it keeps moving in a straight line at a constant speed. When you're in a car that suddenly brakes, your body wants to keep moving forward due to inertia. The seatbelt provides the backward force to stop you. Newton's first law describes what happens when the net force is 0, but what happens when it's not 0? That's Newton's second law of motion. This law quantifies the relationship between force, mass, and acceleration. It states that the acceleration of an object is directly proportional to the net force applied to it, and inversely proportional to its mass. This is famously summarized in the equation acceleration equals net force divided by mass, or more commonly written as F_net equals m times a. Let's break this down. Direct proportionality to force means that if you double the net force on an object, you double its acceleration. If you push a cart twice as hard, it will accelerate twice as much. Inverse proportionality to mass means that for the same net force, an object with more mass will accelerate less. If you apply the same pushing force to an empty cardboard box and a heavy refrigerator, the box, with its smaller mass, will accelerate much more. This law is incredibly powerful and explains so much about the world around us. A major league pitcher can throw a baseball farther than a little leaguer because they can apply a greater force to the ball of the same mass, resulting in greater acceleration and a higher final speed. This equation F equals ma is a cornerstone of physics and a concept you must be comfortable with for your C165 exam. If some of these more advanced concepts feel challenging right now, don't worry at all. That's completely normal, and it's exactly why I created that comprehensive practice question bank. Working through those problems will help solidify your understanding and build your confidence. Newton's third law of motion is perhaps the most often quoted, but also the most frequently misunderstood. It's often stated as, for every action there is an equal and opposite reaction. But this can be misleading. A better way to state it is, whenever one object exerts a force on a second object, the second object exerts a force of equal magnitude and opposite direction on the first object. The crucial, and often missed point, is that these two forces act on different objects. They are an interaction pair. When you push on a wall, that's the action force. The wall pushing back on you is the reaction force. They are equal in size and opposite in direction. They do not cancel each other out because they act on different things. One force is on the wall, the other is on you. It's the force the wall exerts on you that makes you move, if you're on roller skates, for instance. How does a car move forward? The engine makes the tyres turn, and the tyres push backward on the road. That's the action. The reaction is the road pushing forward on the tyres. It is this reaction force from the road that accelerates the car. When a rocket expels hot gas downwards, the gas pushes upwards on the rocket, lifting it into the sky. Every time you walk, you push backward on the ground, and the ground pushes you forward. Newton's third law applies everywhere to every force, whether it's contact forces or forces at a distance like gravity. The Earth pulls on the Moon, and the Moon pulls on the Earth with an equal and opposite force. Now let's talk about a force we experience every single day: friction. Newton's first law says an object in motion stays in motion, but we know if we slide a book across a table, it eventually stops. This is because of friction. Friction is a force that opposes motion between surfaces that are in contact. There are two main types of friction. Static friction is the force that prevents objects from starting to move. When you try to push a heavy refrigerator, you have to overcome a large static friction force to get it going. Once the object is moving, you're dealing with kinetic friction, which is the friction between moving surfaces. Kinetic friction is usually less than static friction, which is why it's often harder to get something moving than it is to keep it moving. Friction isn't always a bad thing. In fact, it's essential. Without friction between your shoes and the ground, you couldn't walk. Without friction, nails would slide out of wood, and you couldn't hold a pen. Car brakes rely on friction to stop the vehicle. Of course, friction also has disadvantages. It causes wear and tear on moving parts and converts useful kinetic energy into wasted heat, reducing the efficiency of engines. We use lubricants like oil to reduce friction. Another ubiquitous force is gravity. Gravity is an attractive force that exists between any two objects with mass in the universe. The more mass an object has, the greater its gravitational pull. We don't notice the tiny gravitational force between ourselves and a coffee cup, because the Earth is so incredibly massive that its gravity completely overwhelms everything else. This is why a dropped pen falls to the floor, not towards your hand. Sir Isaac Newton was the first to realise that the same force that pulls an apple to the ground is the force that keeps the Moon in orbit around the Earth, and the Earth in orbit around the Sun. This is described by his law of universal gravitation. This law states that the force of gravity between two objects is directly proportional to the product of their masses, and, this is the important part, inversely proportional to the square of the distance between them. This inverse square relationship means that distance has a huge effect on gravity. If you double the distance between two objects, the gravitational force between them becomes 1/4 as strong. This is why the Sun, despite being vastly more massive than the Earth, doesn't pull your dropped coffee cup towards it. The Sun is just too far away. Earth's gravity dominates here. Gravity is the force that holds stars and galaxies together and governs the motion of everything in the cosmos. As we wrap up this detailed overview of physics, remember that understanding these concepts is just the first step. The real mastery comes from applying them, which is where those 300 plus free practice questions become invaluable. They're completely free and designed specifically for C165 OA exam success. Let's shift gears from forces to another key concept in physics: momentum. Linear momentum is a measure of an object's motion, often described as mass in motion. It's calculated as the mass of an object multiplied by its velocity. Momentum is a vector quantity, meaning it has both magnitude and direction, just like velocity. The more momentum an object has, the harder it is to stop. A train moving at 20 miles per hour has vastly more momentum than a bicycle at the same speed because of its enormous mass. This is why it takes a train a very long time to stop. One of the most fundamental principles related to momentum is the law of conservation of momentum. This law states that in a closed system, where no external forces are acting, the total momentum before a collision is equal to the total momentum after the collision. Momentum can be transferred from one object to another, but the total amount remains constant. Think of a game of pool. When the cue ball hits another ball, it might stop, transferring all its momentum to the other ball, which then moves off with the same momentum the cue ball had. Or they might both move off in different directions, but the vector sum of their momentums will equal the initial momentum of the cue ball. The toy Newton's cradle, with the swinging silver balls, is a perfect demonstration of momentum conservation. Now let's talk about work and energy, two words we use all the time, but which have very specific meanings in physics. In science, work is done on an object when an applied force causes that object to be displaced or move in the direction of the force. The formula for work is force times displacement. If you push a box across the floor, you're doing work. If you push on a solid wall and it doesn't move, you might feel tired, but you haven't done any work on the wall because there was no displacement. The SI unit for work is the joule. Energy is defined as the capacity to do work or to cause change. Energy comes in many forms. Kinetic energy is the energy of motion. Any moving object has kinetic energy. It depends on both the mass of the object and its velocity. In fact, it increases with the square of the velocity, which is why a high-speed car crash is so much more destructive than a low-speed one. A car going twice as fast has 4 times the kinetic energy. Potential energy is stored energy. There are several types. Gravitational potential energy is the energy an object has due to its position in a gravitational field, basically its height. A book on a high shelf has more gravitational potential energy than one on the floor. Chemical potential energy is stored in the chemical bonds of substances, like the food we eat or the gasoline in a car. Elastic potential energy is stored in objects that are stretched or compressed, like a rubber band or a spring. A cornerstone principle, the law of conservation of energy, states that energy cannot be created or destroyed. It can only be converted from one form to another. When a roller coaster goes down a hill, its gravitational potential energy is converted into kinetic energy. Let's transition from energy and motion to waves. A wave is a repeating disturbance or oscillation that travels from one location to another, transferring energy. A crucial point to remember is that waves transfer energy, not matter. A buoy in the ocean bobs up and down as waves pass, but it doesn't travel to the shore with the wave. There are 2 main categories of waves. Mechanical waves, like sound waves or ocean waves, require a medium, a substance like air, water, or a solid, to travel through. They propagate by causing the particles of the medium to vibrate. Electromagnetic waves, on the other hand, do not require a medium. They can travel through the vacuum of space. Light, radio waves, microwaves, and X-rays are all examples of electromagnetic waves. They are created by oscillating electric and magnetic fields. Waves can also be classified by the direction of their oscillation. In a transverse wave, the particles of the medium oscillate perpendicular or at a right angle to the direction the wave is travelling. If you shake one end of a rope up and down, you create a transverse wave that travels along the rope. The wave moves horizontally, but the rope segments move vertically. All electromagnetic waves are transverse. In a longitudinal wave, the particles of the medium oscillate parallel to the direction the wave is travelling. Imagine pushing and pulling one end of a slinky. You create areas of compression where the coils are close together, and areas of rarefaction or expansion where they're spread apart. This series of compressions and rarefactions travels along the slinky. Sound is a perfect example of a longitudinal wave. A speaker vibrates back and forth, creating compressions and rarefactions in the air that travel to your ear. Every wave has several key properties you need to know. The amplitude is the maximum displacement from the equilibrium or rest position. For a water wave, it's the height from the normal water level to the crest, the highest point, or to the trough, the lowest point. Amplitude is related to the energy of the wave. A higher amplitude means more energy. Wavelength, represented by the Greek letter lambda, is the distance between two consecutive identical points on a wave, like from crest to crest or trough to trough. It's the spatial length of one full cycle. The period is the time it takes for one complete wave to pass a point, and frequency is the number of waves that pass a point in a given amount of time, usually 1 second. The unit for frequency is the hertz. Ease. Frequency and period are inversely related. A high frequency means a short period, and vice versa. The speed of a wave is equal to its frequency multiplied by its wavelength. Now let's focus on the electromagnetic spectrum. This is the entire range of electromagnetic radiation, organised by wavelength and frequency. Remember, for EM waves, a longer wavelength means a lower frequency and lower energy, while a shorter wavelength means a higher frequency and higher energy. At the long wavelength low energy end, we have radio waves used for broadcasting. Next are microwaves used in communication and for cooking. Then comes infrared radiation, which we feel as heat. After that is the very narrow band of visible light, the only part of the spectrum our eyes can see. We perceive different wavelengths of visible light as different colours, from red at the long wavelength end to violet at the short wavelength end. A rainbow is a natural display of the visible spectrum. Beyond visible light with increasing energy, we have ultraviolet, UV light from the sun, which can cause sunburns. Then come X-rays, which are high energy enough to pass through soft tissues, allowing us to image bones. And at the highest energy, shortest wavelength end are gamma rays, produced by nuclear reactions and cosmic events. Each part of the EM spectrum has unique properties and applications, from communication and medical imaging to astronomy. You'll want to be familiar with the order of the spectrum and the general characteristics of each region for the C165 OA exam. Now we pivot from the world of physics to the realm of chemistry, the science of matter and its changes. Everything in the universe is made of matter or energy. Matter is anything that has mass and takes up space. Mass, as we discussed in physics, is the measure of the amount of stuff in an object, and its SI unit is the kilogram. It's constant regardless of location. Weight is the force of gravity on that mass. At the most fundamental level, all matter is composed of atoms. An atom is the basic building block of matter, the smallest unit of a substance that still retains the properties of that substance. Atoms are incredibly tiny and are themselves made of even smaller subatomic particles, protons, neutrons, and electrons. The protons and neutrons are located in a dense central core called the nucleus. Protons have a positive electrical charge, while neutrons are neutral with no charge. The electrons, which have a negative charge, exist in a cloud or shells outside the nucleus. In a neutral atom, the number of positive protons is exactly balanced by the number of negative electrons. The mass of an atom is almost entirely concentrated in the nucleus, as protons and neutrons are about 2,000 times more massive than electrons. The electrons in the outermost shell of an atom are called valence electrons. These are the most important electrons in chemistry because they are the ones involved in forming chemical bonds and participating in chemical reactions. A substance composed of only a single type of atom is called an element. There are 92 naturally occurring elements on Earth, and each is defined by the number of protons in its nucleus. This is called the atomic number. Every atom of oxygen has 8 protons. Every atom of gold has 79 protons. If an atom had 7 protons, it would be nitrogen, not oxygen. The periodic table is a masterful chart that organises all the known elements based on their atomic number and chemical properties. Elements in the same vertical column, called a group, have the same number of valence electrons and therefore tend to have similar chemical behaviours. But most substances we encounter are not pure elements, they are compounds. A compound is a substance formed when two or more different elements are chemically bonded together in a fixed ratio. Water, H2O, is a compound made of hydrogen and oxygen atoms bonded in a 2-to-1 ratio. Carbon dioxide, CO2, is a compound of carbon and oxygen in a 1-to-2 ratio. The smallest unit of a compound is a molecule. A molecule is a group of atoms held together by covalent bonds. It's important to distinguish between pure substances and mixtures. A pure substance consists of only one type of element or one type of compound. Pure gold and pure water are pure substances. A mixture, on the other hand, is a combination of two or more pure substances that are not chemically bonded. In salt water, the salt, sodium chloride and water molecules are mixed together, but they haven't formed a new compound. You can change the ratio of salt to water, and it's still salt water. There are two types of mixtures. A homogeneous mixture is uniform throughout, like salt water or clean air. You can't see the individual components. A heterogeneous mixture is not uniform, like sand and water. Or a pizza. You can see the different parts. Matter can exist in different states, most commonly as a solid, liquid or gas. The state of a substance depends on the energy of its particles and the strength of the forces between them. In a solid, particles are packed tightly in a fixed arrangement. They have low energy and can only vibrate in place. This is why solids have a fixed shape and a fixed volume. In a liquid, particles have more energy. They are still close together, but they can slide past one another. This is why liquids have a fixed volume but take the shape of their container. In a gas, particles have very high energy and are far apart, moving randomly and rapidly. The forces between them are very weak. This is why gases have no fixed shape or volume. They expand to fill whatever container they are in. The transition between these states is a physical change. A physical change alters the form of a substance, but not its chemical identity. Melting ice is a physical change. The H2O molecules are still H2O molecules. They're just arranged differently. Other physical changes include dissolving sugar in water or crushing a can. A chemical change or chemical reaction is a process that results in the formation of new substances with a different chemical composition. When wood burns, it reacts with oxygen to form new substances like ash, carbon dioxide and water vapour. The original wood is gone. Signs of a chemical change often include the production of a gas, bubbling, a change in colour, the formation of a solid, a precipitate, or the production of heat or light. In a chemical reaction, the starting materials are called reactants, and the new substances formed are called products. Now let's explore how atoms connect to form compounds. This happens through chemical bonds, which are attractive forces that hold atoms together. There are three main types of chemical bonds you should know for the C165 OA exam: ionic, covalent and metallic. Ionic bonds typically form between a metal and a non-metal. Metals tend to lose their valence electrons easily, while non-metals tend to gain them. In an ionic bond, one or more electrons are completely transferred from the metal atom to the non-metal atom. When an atom loses electrons, it has more protons than electrons and becomes a positively charged ion. When an atom gains electrons, it has more electrons than protons and becomes a negatively charged ion. The strong electrostatic attraction between these oppositely charged ions is what forms the ionic bond. Table salt, sodium chloride, or NaCl, is a classic example. A sodium atom transfers its one valence electron to a chlorine atom. Sodium becomes a positive Na+ ion, and chlorine becomes a negative chlorine. These ions then form a crystal lattice structure. Covalent bonds, on the other hand, typically form between two non-metal atoms. Since both non-metals want to gain electrons, neither one can win the tug of war, so instead they share one or more pairs of valence electrons. This shared pair of electrons is attracted to the nuclei of both atoms, holding them together in a stable molecule. This sharing is the essence of a covalent bond. Water, H2O, is a great example. Oxygen needs 2 more electrons to have a full outer shell, and each hydrogen needs 1. So the oxygen atom shares a pair of electrons with each of the 2 hydrogen atoms. These shared electrons form the covalent bonds. Finally, metallic bonds are found in metals. In a metal, the valence electrons are not held tightly by any single atom. Instead, they form a sea of delocalized electrons that move freely throughout the entire metal structure, surrounding a lattice of positive metal ions. This mobile sea of electrons is what makes metals such an excellent conductor of electricity and heat, and also gives them their properties of malleability and ductility. The periodic table is not just a list of elements, it's a powerful tool for predicting their properties and how they will bond. As we said, elements are arranged in columns called groups and rows called periods. Elements in the same group have the same number of valence electrons, which is why they have similar chemical properties. For example, the elements in group 1, the alkali metals, all have 1 valence electron and are highly reactive metals that tend to lose that electron to form a +1 ion. The elements in group 17, the halogens, all have 7 valence electrons and are highly reactive nonmetals that tend to gain 1 electron to form a -1 ion. Group 18 contains the noble gases, which have a full outer shell of valence electrons. This makes them very stable and unreactive. The periodic table also has a general organisation of element classes. The left side and centre are dominated by metals, which are typically shiny, solid, malleable, and good conductors. The upper right corner contains the non-metals, which are variable in state, solid, liquid, or gas, and are generally brittle and poor conductors. A staircase line separates the metals from the non-metals, and along this line we find the metalloids, which have properties intermediate between metals and non-metals. Silicon, a key component in computer chips, is a famous metalloid. One of the most fundamental laws in chemistry is the law of conservation of mass. It states that matter cannot be created or destroyed in a chemical reaction. The total mass of the reactants must equal the total mass of the products. Atoms are simply rearranged during a reaction. None are lost and no new ones are created. If you burn 12 grams of carbon with 32 grams of oxygen, you will produce exactly 44 grams of carbon dioxide. The mass is conserved. This is why chemists use balanced chemical equations. In a balanced equation, the number of atoms of each element on the reactant side is equal to the number of atoms of that element on the product side. This reflects the conservation of mass at the atomic level. Now let's connect chemistry back to energy. Temperature, as we've discussed, is a measure of the average kinetic energy of the particles in a substance. The faster the particles are moving or vibrating, the higher the temperature. Thermal energy is the total energy of all the particles in an object due to their random motion. A large swimming pool at 25 degrees Celsius has much more thermal energy than a small cup of water at the same temperature, simply because it contains vastly more water molecules. Heat is the transfer of thermal energy from a warmer object to a cooler object. When you add ice to a warm drink, heat flows from the drink to the ice. This transfer of thermal energy can cause phase changes. Melting is the change from solid to liquid. Freezing is the change from liquid to solid. Evaporation is the change from liquid to gas. And condensation is the change from gas to liquid. Importantly, these phase changes involve energy. It takes energy to melt ice or boil water because you have to supply energy to overcome the forces holding the molecules together. This is why sweating cools you down. As the sweat evaporates from your skin, it absorbs heat from your body. Conversely, when a gas condenses or a liquid freezes, energy is released. This is why a steam burn is so severe. When the steam condenses to liquid on your skin, it releases a large amount of energy. Now let's zoom out from the atomic and molecular scale to the scale of our planet and the cosmos in our Earth and Sky section. The driving force behind the structure of the universe is gravity. The prevailing scientific theory for the origin of the universe is the Big Bang theory, which states that about 13.8 billion years ago, the universe began as an infinitesimally small, hot, dense point that expanded rapidly. In the immediate aftermath, the simplest elements, hydrogen and a smaller amount of helium, were formed. Over millions of years, gravity began to pull these vast clouds of gas and dust together. In regions where the density was slightly higher, the gravitational pull was stronger, attracting more and more matter. This process, called gravitational collapse, led to the formation of the first stars. As a star forms, the pressure and temperature at its core become so immense that nuclear fusion begins. This is the process where light atomic nuclei, like hydrogen, are forced together to form heavier nuclei, like helium, releasing a tremendous amount of energy. This is what makes stars shine. All the heavier elements in the universe, like the carbon in our bodies and the iron in our blood, were forged inside stars through nuclear fusion over billions of years. These stars are not scattered randomly throughout the universe. They are clustered together by gravity into enormous structures called galaxies. Our solar system is part of the Milky Way galaxy, which contains hundreds of billions of stars, and there are hundreds of billions of other galaxies in the observable universe. At the centre of most large galaxies, including our own, lies a supermassive black hole, an object with such immense gravity that not even light can escape. Our solar system consists of our star, the Sun, and all the objects that orbit it due to its gravity. This includes 8 planets, their moons, asteroids, and comets. The planets are divided into 2 groups. The 4 inner planets, Mercury, Venus, Earth, and Mars, are small, dense, and rocky. The 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, are giant, low-density planets made primarily of gases like hydrogen and helium. This division is a result of how the solar system formed. Near the hot, young Sun, only rocky and metallic materials could condense, while lighter gases were blown to the outer regions. All the planets orbit the Sun in the same direction and on roughly the same plane, a remnant of the original rotating disk of gas and dust from which they formed. Let's focus on our home planet, Earth. The regular cycle of seasons, warm summers and cold winters, is not caused by Earth's changing distance from the Sun. In fact, in the northern hemisphere, we are slightly closer to the Sun in winter. The real reason for the seasons is the tilt of Earth's axis of rotation, which is about 23.5 degrees. As Earth orbits the Sun over the course of a year, this tilt means that different parts of the Earth receive the Sun's rays more directly at different times. When the northern hemisphere is tilted towards the Sun, it receives more direct, concentrated sunlight, leading to longer days and warmer temperatures. That's summer. At the same time, the southern hemisphere is tilted away, receiving less direct sunlight, resulting in shorter days and winter. 6 months later, the situation is reversed. The regions near the equator experience very little seasonal temperature change because they receive relatively direct sunlight all year round. Beneath our feet, the Earth is not a solid ball, but is composed of several layers. The outermost thin, rocky shell is the crust. Below that is the mantle, a thick layer of hot, solid rock that can flow very slowly over geologic time. The very centre of the Earth is the core, which is made of iron and nickel. The outer core is so hot that it's a liquid, while the immense pressure at the very centre keeps the inner core solid. The surface of the Earth is constantly being shaped and reshaped by processes of weathering, erosion, and deposition. Weathering is the breakdown of rock in place, either physically, like water freezing in cracks and expanding, or chemically, like acid rain dissolving certain minerals. Erosion is the transportation of that weathered material by agents like flowing water, wind, glaciers, or gravity. Rivers are powerful agents of erosion, carving out canyons like the Grand Canyon over millions of years. Deposition is the process where this eroded material is dropped in a new location, forming features like river deltas or sand dunes. These processes are part of a grand, continuous process called the rock cycle. There are 3 main types of rocks. Sedimentary rocks are formed from the accumulation and cementation of weathered particles or sediments like sand, silt, and clay. They often form in layers and can contain fossils, Igneous rocks are formed from the cooling and solidification of molten rock. Magma that cools slowly underground forms coarse-grained igneous rocks like granite, while lava that erupts and cools quickly on the surface forms fine-grained rocks like basalt. Metamorphic rocks are rocks that have been changed by heat, pressure, or chemical reactions. For example, limestone, a sedimentary rock, can be metamorphosed into marble. The rock cycle illustrates how any type of rock can be transformed into any other type over geologic time. An igneous rock can be weathered into sediment to form a sedimentary rock, which can then be subducted and melted to form a new igneous rock. Geologists read Earth's history in these rock layers. The principle of superposition states that in an undeformed sequence of sedimentary rocks, the oldest layers are at the bottom and the youngest are at the top. The principle of cross-cutting relationships states that if a feature, like a fault or an igneous intrusion, cuts across rock layers, it must be younger than the layers it cuts. Fossils, the preserved remains or traces of ancient organisms, are also invaluable tools. They tell us about the types of life that existed in the past, how they evolved, and when mass extinction events occurred. The fossil record is like a book with many missing pages, but it still provides a rich history of life on Earth. One of the most important theories in all of Earth science is the theory of plate tectonics. This theory explains that Earth's crust and the upper part of the mantle are broken into large pieces called tectonic plates, which are slowly moving over the mantle below. This idea began as continental drift, proposed by Alfred Wegener in the early 20th century. He had strong evidence like the puzzle-like fit of continents, matching fossil records, and similar rock formations across oceans. However, he couldn't explain how the continents moved, so his idea was largely dismissed. The key evidence came decades later from mapping the ocean floor. Scientists discovered the mid-ocean ridges, underwater mountain ranges where new oceanic crust is being formed and spreading outwards. This process, called seafloor spreading, provided the mechanism for continental movement. The continents are essentially passengers on these moving plates. The interactions at the boundaries between these plates are responsible for most of Earth's major geological activity. Like earthquakes and volcanoes, at divergent boundaries, plates are moving apart, and magma rises to form new crust, like at the mid-ocean ridges. At convergent boundaries, plates are colliding. If an oceanic plate collides with a continental plate, the denser oceanic plate sinks, or subducts, beneath the continent. This process creates deep ocean trenches and chains of volcanoes along the coast, like the Andes Mountains. If two continents collide, they crumple and are forced upwards, creating massive mountain ranges like the Himalayas. At transformed boundaries, plates slide past each other horizontally. The San Andreas Fault in California is a famous example. The stress that builds up along these boundaries is released in the form of earthquakes. The ring of fire around the Pacific Ocean is a zone of intense volcanic and earthquake activity because it's lined with many convergent plate boundaries. Now let's look up at the blanket of gases surrounding our planet, the atmosphere. Earth's atmosphere is composed of about 78% nitrogen, 21% oxygen, and about 1% other gases, including argon and trace amounts of carbon dioxide and water vapour. The atmosphere is divided into layers based on temperature changes with altitude. We live in the troposphere, the lowest layer, where all weather occurs. Temperature decreases as you go up in the troposphere. Above that is the stratosphere, which contains the vital ozone layer. The ozone layer absorbs harmful ultraviolet radiation from the sun, causing the temperature to increase with altitude in this layer. Above the stratosphere are the mesosphere, thermosphere, and the outermost exosphere, which gradually fades into space. Uneven heating of the Earth's surface by the sun creates differences in air pressure, which drives wind. Warm air is less dense and rises, creating areas of low pressure. Cool air is denser and sinks, creating areas of high pressure. Air flows from high pressure to low pressure, creating wind. On a global scale, this creates large convection cells. However, because the Earth rotates, this air movement is deflected. This is called the Coriolis effect. In the northern hemisphere, moving objects are deflected to the right, and in the southern hemisphere, they are deflected to the left. This effect breaks up the large convection cells into smaller ones and creates the prevailing wind patterns we see on Earth. The boundaries between large air masses of different temperatures are called fronts. A cold front, where cold air ploughs under warm air, often brings strong storms. A warm front, where warm air slides over cold air, typically brings lighter, more prolonged precipitation. Storms like thunderstorms, tornadoes, and hurricanes are all powerful weather phenomena driven by the movement of energy and moisture in the atmosphere. Water is essential to life and to many of Earth's processes. The continuous movement of water on, above, and below the surface of the Earth is called the hydrologic cycle, or water cycle. Water evaporates from oceans and lakes, rises as water vapour, condenses into clouds, and falls back to Earth as precipitation like rain or snow. This water can then become runoff into rivers, or infiltrate the ground to become groundwater. Over 97% of Earth's water is salt water in the oceans. Of the small amount of fresh water, most is locked up in glaciers and ice caps. Finally, let's discuss Earth's climate and energy. The Earth is kept warm enough for life by a natural process called the greenhouse effect. Solar energy warms the Earth's surface, which then radiates heat back out. Certain gases in the atmosphere, called greenhouse gases like water vapour, carbon dioxide and methane, trap some of this outgoing heat, warming the planet. This is a good thing. Without it, Earth would be a frozen wasteland. However, since the Industrial Revolution, human activities, primarily the burning of fossil fuels like coal, oil, and natural gas, have released enormous amounts of extra carbon dioxide into the atmosphere. This has enhanced the natural greenhouse effect, leading to a steady increase in global average temperatures, a phenomenon known as global warming. The effects of this include melting glaciers and ice caps, rising sea levels, and more extreme weather events. In response, there is a growing focus on renewable energy sources that do not produce greenhouse gases. These include solar power, which uses photovoltaic cells or thermal systems to capture energy from the sun; wind power, which uses turbines to convert the kinetic energy of wind into electricity; hydroelectric power from dams; geothermal energy, which taps into the Earth's internal heat; and biomass energy, which is derived from organic matter. Each has its own advantages and disadvantages, but together they represent a path towards a more sustainable energy future. We have covered a tremendous amount of ground today, from the smallest particles to the largest structures in the universe. We've seen how the laws of physics, like gravity and conservation of energy, govern everything. We've explored how these laws dictate the interactions of atoms in chemistry, leading to the vast diversity of matter we see. And we've learned how these same physical and chemical principles shape our planet, driving plate tectonics, weather, and the rock cycle. The key to succeeding on your C165 OA exam is to see these connections. Don't just memorise isolated facts. Understand how force leads to acceleration, how that acceleration plays a role in planetary orbits, how planetary conditions allow for certain chemical processes, and how those processes shape the world. You have a solid foundation now. The next crucial step is to practice. Don't forget to grab those free practice questions from the link in the description. With the depth of knowledge you've gained today, plus the practice from those questions, you'll be incredibly well prepared for your OA exam. You've got this. Good luck.